Thank you, Blas, also for the invitation to come here. Very nice to be here. I always like talks to be interactive, so if you have any questions, don't wait till the end. Please interrupt me at any time if you want to have some more clarity about that. Now I want to talk about correlated metals. So this whole workshop is about correlated quantum systems, but specifically I want to talk about, well, metals. So what is a metal? In condensed matter, the typical word metal is something different than in, say, astronomy or chemistry. In condensed matter, we mean a metal is a system that conducts electricity well, as opposed to an insulator that doesn't conduct electricity well. Now, that is a very vague statement, and actually you can only make that statement precise at zero temperature, because then an insulator is absolutely not conducting, so the conductivity is zero at zero temperature, whereas a metal has then a finite conductivity at zero temperature. So at any finite temperature, it's kind of difficult to tell which is a metal or which is an insulator, but the traditional picture just starts from the zero temperature limit and then says, well, if you're in an insulator, of course, conductivity is zero, resistivity therefore infinite at zero temperature. Therefore, once you raise the temperature, it can only go down. So the dr dt is negative in an insulator. And indeed, most insulators have this behavior that the resistivity has this activated behavior, this e to the delta over t, see here, which is the case for standard band insulators, of course. And on the other hand, if you're a metal at zero temperature, there's some residual resistivity. The moment you turn on temperature, so you raise the temperature, more and more scattering processes come in, electron scattering, electron photon scattering, and stuff like that. So typically the resistivity increases. So at finite temperature, the traditional theory says metals and insulators can be separated by just looking at the derivative of the resistivity versus temperature. And if you then have an actual transition between a metal and an insulator, the most natural thing that you can have is something in between that's constant. And in two-dimensional systems that I like for a variety of reasons, but in two-dimensional systems, then the resistivity just has the same dimensions as the resistance. And it's natural to say that, okay, at this critical point between a metal and an insulator, you would have just the quantum of resistance, which is then a constant at all temperatures. So that's the standard picture, traditional. If you look at older books, for example, a book from Vlad, it's explained also there. But I'm very inspired by a lot of developments that went on in moire materials, and I don't think I need to explain what all these twisted materials are. I'm just going to show you some results. And already in one of the first results in twisted bilayer graphene, they talk about the system that's insulating, quote unquote. But then if you look at the slope, so the way that you can see this is you have here the conductance in a log scale and the inverse of temperature. So this activated behavior should be a straight line. But, and then low temperatures to the right. So it looks like a little bit of insulating here, but then it kind of becomes more conducting than you would expect for an insulator. So is this an insulator or not? A more extreme case is, for example, this result in twisted bilayer tungsten diselenide, where again you have now it's the log of the resistance instead of the log of the conductance. So, but still with the inverse temperature, activated behavior should be a straight line. And rather than having a continuously growing resistivity following the activated behavior, kind of flattens out. So are these insulators or are these metals? We don't really know. So this started to think about it. And the nice thing about these moire materials is that you can not only have these single curves, but you can have a whole family of curves because you can tune something about the material. So this is a result from aligned TMD heterobilayer called molybdenum ditelluride tungsten diselenide.
Excuse me, look, I just want to mention that this fake insulator, I mean, this has been known or seen in like dope silicon.
Oh yeah,
even in 3D. So
I will get there. Yes.
Okay.
No. So I will get to the point of MOE correlations, which also have the RDTs negative and things like this.
Yeah, and the 2D electron gas also in
the 2D
the silicon and others even before moire ever appeared.
Yes. I 100% agree. But if you look at this data and you ask the people who took this data how to interpret this.
Okay, that's a different matter.
So this is one of the things, right? So I 100% agree. I think we 100% agree. Yeah. We just have to do some missionary work to emphasize that just looking at DRDT is not giving you the answer whether it's an insulator or metal. But if you look at the traditional picture and you look at the data like this, so here they can tune the electric field, and what the electric field does, it basically closes the gap between different bands. So this is not much correlated, it's just weakly correlated stuff. So you have bands, you tune electric field, the gap is closed. So you should have a transition from something that's conducting, like to something that's metallic, to something that's insulating. So indeed, if you put all these curves on one plot, you see these dark blue curves, that really looks like your prototypical metal. It just has some residual resistivity, and then it goes up as you increase temperature. I don't even know how to call this color, like light brownish color, has a very clear activated behavior. It just shoots up as you go down in temperature. And then the traditional picture is like, okay, well, there's some curve, like probably this one with the little crosses here, that is more or less flat. So that is where the transition happens. That's where my gap closes. But I disagree, and I think I would also probably disagree where you have to put this. So let's look at the theory, like let's do the actual calculation. What would you expect if you just close these gaps? And for that, the thing that I really like to do is not Boltzmann theory, but just Kubo theory, which is just linear response theory, just a little bit going through the details. If you ignore vertex corrections, which you can ask me about once I finish this slide if you want, the key of the Kubo formula is that you need the density of states of your electrons, both in momentum and energy, and you have the current operator, and you take the product of two density of states, two current operators, and then you have the derivative of the Fermi function that tells you how it works as a function of temperature. And if we apply this Kubo formula to this exact case where you have an insulator, namely a gap, or you have the bands that are overlapping, the thing that you can put in is just the density of states with the dispersions given by here, this animated thing on the left, and just some disorder, for example. Some scattering mechanism that's captured by the self-energy of the electron. And the simplest case is just say, let's have some 1 over tau scattering rate. If you plug that in, at 0 temperature, you automatically get Drude's formula, which is nice. So, it's a method that works. Drude's formula, of course, is the 0 temperature conductivity is particle density, scattering rate divided by the effective mass of your electron. If you look at the system in more general, so not just at 0 temperature, but at all temperatures, and you have here this gap, which is characterized, I just call this EF, so it's negative if they overlap and positive if they don't overlap. Kubo formula gives you exactly this formula. And indeed, now, if I put this tau in here and I allow this tau also to have some temperature dependence, for example, I include some phonon scattering or whatever, I can get this nice series of curves. But what's interesting to note is that while on the insulating side, this formula reduces to nice activated behavior, if I set the bands to be touching, so EF goes to 0, I actually just get a linear in T conductivity, or in other words, the resistivity diverges as a power law. There's a 1 over T diverging resistivity at the critical point. So at the critical point, it's not flat, it actually turns up. And then it's actually a natural consequence that on the metallic side, there's therefore a region in my parameter space at temperature where the dr dt is actually negative, even though I'm on the metallic side, even though I have overlapping bands. And this is actually what I think you see a lot of materials where you have a dr dt negative, is just very close to a metal insulator transition. So this is fake insulator regime that we think we have. The beauty of this formula is that it's also a scaling formula, meaning that the conductivity is just of this form. This is a general scaling form, namely you have some temperature to some power and a function that only depends on our tuning parameter divided by temperature. If you have a function like this, in this case, this alpha is 1, so it's not a very complicated scaling function. But what it means is that I can plot T on the horizontal axis, temperature divided by my scale, how far I am from the transition, so EF or mu, whatever you want to call it. And I divide it by the curve at the critical point, so this 1 over R diverging resistivity, then all the curves on the insulating side and all the curves on the metallic side, they collapse onto their respective branches, right? So it's a general scaling behavior. And it's kind of funny because there's no order parameter symmetry breaking associated with that, which is usually what you want if you have universal behavior related to scaling. So this is a transition, but it's just not one of your Landau phase transitions. Yet it does show scaling.
I'm a bit confused. Can you go back to, so there's one curve which is non-monotonic. How can you get this to become monotonic if you do a division?
Right.
So you divide by the transition, I guess, the black curve.
Yeah.
So this, the one that you're now pointing at, how do you get this to fall onto either of these two lines? Because it's no monotonic, it goes up and down.
Yeah, because this black one diverges.
No, the one with the maximum.
Yeah, no,
that
but
one, right?
I know, but if you have something that's non monotonic and you divide it by something that's diverging, it can collapse onto something that's, I mean, these guys also have kind of a bump, right? You can see how this bump develops as you go closer to the critical curve.
Just to understand, so what are the scattering mechanisms here that you're considering to produce these scaling curves?
So we're agnostic towards the scattering mechanism, because the only thing that enters into this formula is the scattering, and that's something that's end up front here. So I can make anything here in the scattering mechanism that I want.
So let me rephrase the question. Are you considering a constant imaginary self-energy as it's written in the previous slide, so that gives you tau?
No.
And then the temperature dependence comes just from the occupation of states, the Fermi-Dirac. Okay, so then I'm fine also with the absence of vertex corrections, because then you don't have momentum dependence to self-energy. That's why.
Exactly.
Okay.
So this is kind of a local picture. So it is. So we started with the simplest thing, and why we think it's relevant is because it actually works for material systems. So this is the same plot that I had for the molybdenum, the telluride, tungsten selenide before, where there was a curve that's more or less flat, but now we say, no, this curve that's like 1 over r diverging, that is where the critical point is. And the nice thing is, if we divide all the curves by this critical curve, you do get scaling collapse. And not only that, you not only get the scaling collapse, the collapse is exactly onto these dashed lines, which are our analytical formula of the previous slide. So this is not the only thing. We started looking at other moire systems. So for example, this very complicated sandwich with a tungsten selenide bilayer graphene and another tungsten selenide layer, which had been explained as some kind of resistivity transition. So this is the raw data of that system. But interestingly, if you look at this, it never really becomes really insulating, right? This is exactly this type of fake insulating behavior that we described, that it goes up and then it kind of flattens out. And this is something that naturally then can be understood with our picture, that the actual, if there would be if you would somehow tune this further towards a metal insulator transition, that would be the black dashed line here. Dividing by this black dashed line, we can collapse all these curves onto one single curve. So every curve here is on the metallic side.
So here the black dashed line, this is not data. This is not data. Something you've computed.
Yes.
But on the left side plot,
that's just
black curve. Data. That's data that's. And how did you identify that this was the right line for you?
Also, there's the most kind of, how shall I say it, blind way to do this. So not to put in your own assumptions, is you can quantify how well the scaling collapse is, and then just try to do the scaling collapse with different critical curves. And then you take the one that's the best scaling collapse. And that happens to be also a curve that looks very much like 1 over r. So r is 1 over t.
If we go back to the calculation you've done.
One more.
Yeah, resonating with some of the discussions we've had in the past. So here you don't need to worry about whether this scattering assumption violates charge or say energy conservation, because there are no vertex corrections.
Yeah, so the beauty is that's not something that you have to worry about in the current correlation function compared to our discussion with density correlation function. So this is, I think, one way that I understand it, it comes from a Ward identity, that if you only have a local self-energy, this does not affect the vertex of the current correlation function. But if you only have a local self-energy, the current vertex is not changed by the self-energy. But the density vertex is.
Can I ask a question about the logic of this presentation, which I think is beautiful? After you have concluded that the insulators, the so-called insulators are actually fake insulators, okay, then why continue to use that fake label throughout the rest of the presentation?
I'm not. I'm gonna remove
Well,
it.
you are. It says MIT right there on the.
Oh, but this is okay. So this one is not an MIT. This one is right. This has real insulating curves.
Okay,
It's just
let's go back to the previous slide. So now you have provided a definition of fake. Okay, so could you provide a definition of real?
A real insulator is an insulator that has a gap in its excitation spectrum.
Okay, fine. I agree.
Okay.
In the equation that we see above, the central assumption is that the scattering time is not related to the Fermi, to the energy gap.
Yeah.
So basically, when the scaling matches, it means that no matter what is the energy gap, the scattering time is the same for all these parts.
Yeah, that can be changed. That, of course, can be violated. So I'm not saying this happens in every system. But yeah. Good point. In real systems, just the final MIT that I wanted to show is this GST, which is a three-dimensional material, germanium, antimony, telluride, if I remember correctly. These are materials that are very disordered, and the exact resistivity that you have depends on the history of how you make it. So it's a bit of a weird material. However, this raw data here at very high temperatures, so 400 to 600 Kelvin, shows that there is also different curves depending on the history of your maker. And then this also looks like a very nice metal to insulator transition, which again, we can identify where the critical curve is, and then do the collapse onto this. Now, as Dragana pointed out, materials with DRDT negative or metals with DRDT negative is something that's actually already known for quite a long time. And one of the things that was early on in 73 observed by Moy was that in metals at very high temperatures, so here this is like 200 to 1000 Kelvin, he was studying various titanium aluminum alloys with different concentrations of aluminum and titanium. And there you can see that depending on the precise concentration, you have curves that look very traditionally metallic with DRDT positive, but also curves that are definitely conducting well, but the DRDT would be negative. And he observed that if you can define a dimensionless measure of this derivative, which he called alpha, just T over R times DRDT, which is therefore dimension, that thing correlates with the actual resistivity of the material. And these are called Moy correlations, and that's been for quite a while a kind of mystery is a bit big word, but it was not completely understood why this correlation is so strong. Within our theory, we can say, okay, this is kind of, we're looking now at the high temperature limit, but still close to a metal insulator transition. So at high temperatures, at, well, 200 to 1000 Kelvin, probably the scattering mechanism is dominated by electron phonal scattering, and in that regime, it's a linear in T phonal scattering. So let's put that in our scattering rate that has just some disorder component and a electron phonal coupling, which we characterize by lambda. Plug that into our scaling theory and then calculate what this alpha DRDT is, we get this expression, which indeed only depends on R itself. So the nice thing is we can take this formula, plot exactly what Moy was plotting. So the dark blue dots are the original Moy data, and our black line seems to follow that pretty well. So we do think that we can understand Moy correlations as just being close to this metal insulator transition where you can have DRDT negative, even though you're on the metallic side of the transition. So not only this titanium aluminum compounds of Moy make sense in that regard. We look at various other materials, for example, this molybdenum ditelluride tungsten dicellulide. We can calculate the same dimensionless coefficient alpha versus R, and they all collapse onto the same curve. So we do think that there's some universal behavior in many materials that are, when you're close to metal insulator transitions, you can see this DRDT negative, and yeah, I think it pretty well fits the original Moy correlation. So I think we kind of cracked that problem.
So lambda is a free parameter in your fitting, or lambda?
Yes.
It's not related to some measure, independent measure or what?
So the lambda we can kind of independently measure. So by looking at these curves, Like you have a set of curves, and they kind of all seem to go to an infinite value at infinity, and that sets the lambda. So it's not just a fitting function. It's sort of, well, I mean, it is a fit.
But by the way, the alpha that you define here has nothing to do with the alpha you use for your scaling function.
Oh yeah, exactly. Different alpha.
No, yes. I was
Historical
beginning, I was confused,
coincidence. Yeah, I just used the same letter as Moya, like here, used the alpha. No, we just call it D over R drdt. Okay. So that all, I promised you to talk about correlated metals, but so far I didn't actually talk much about correlation. So let's switch it up and look at metal insulator transitions that are due to correlations. So in this molybdenum dithaloride tungsten selenide that I all started with, that transition was a band transition. So you need 2 electrons per unit cell, and then you can have a transition from a metal to a band insulator. In the same class of materials, these moire materials, you can also just go to integer filling, like 1 electron per moire unit cell, and then the same logic, you can tune the electric field and thereby induce a transition from a metal to a Mott insulator. Because if you're at integer filling, like odd integer filling, it has to be a Mott insulator. So specifically the same sample, but then looking at integer filling 1 instead of filling 2, you also have a transition that's nicely and smooth, going from something that looks very much like a metal to something that very much looks like a nice activated insulator, and some interesting stuff in between. And it looks very smooth and continuous. Now, the observation of a continuous Mott transition is actually theoretically kind of problematic. If you look back into Mott's original book, he discusses, for example, the vanidates. There, the Mott transition is a first order transition because, as we've seen, there's no symmetry difference between metals and insulators, so a transition between the two should be first order, like between water and gas. And that's exactly how the phase diagram looks like. You have a first order line, a critical endpoint. On one side it is insulating, and then the other side is metallic. At high temperatures, there's like a crossover between these guys. Moreover, in many Mott insulators, at low temperatures, the Mott insulating state becomes antiferromagnetic. Therefore, it becomes an antiferromagnetic insulator. But on the metallic side, you can have like a spin density wave instability, and you're also ending up at an antiferromagnetic insulator. And therefore, at low temperatures, you're just an antiferromagnetic insulator, and there's no way in telling whether you are a Mott insulator or actually just a metal that has become an antiferromagnetic insulator. So Mott criticality cannot be, because it's supposed to be first order, and it's supposed to be hidden by antiferromagnetism anyway. Yet we see it in these materials. Well, one of the things that is kind of nice is these are triangular lattice systems, so you expect that at least antiferromagnetism is suppressed a lot compared to your square lattice antiferromagnets. But if I compare it to our band insulating picture before, we do see a power law critical curve, but now just with a different power. Now alpha has the power again. We again have a regime where drdt is negative close to the transition, but on the metallic side, the insulator has a gap that continuously vanishes. But the most important differences is that all the exponents that we see in this Mott insulating case are different than the exponents that I showed for the band insulating case. And on the Mott metallic side, there's an interesting Fermi liquid-like regime where you can see mass enhancement. So I just wanted to zoom in a bit on this because this is the correlated metals that I promised you in the title. Just about Mott criticality, together with Vlad Dobrosaglevich, we looked at, and you think Tang, we looked at like theories of this Mott criticality, because clearly, if you just open Mott's book, it's not there. And there's various theories. Most importantly, there is a theory that says you need to suppress antiferromagnetism, otherwise you can't see the transition. If you suppress antiferromagnetism, the only thing that is possible for a state with 1 electron localized per unit cell is a spin liquid. So you must have some spin-on theory.
Previous slide. So is there evidence that this thing is an antiferromagnet?
There's no evidence of antiferromagnetism.
So what's the basis for saying that you think it's a classical Mott transition?
You're at infilling 1.
I see. It's your experimentalist colleague told you what they think the charge.
Oh yeah, no, but you can really.
I'm asking for empirical evidence. So is there any empirical evidence that it's a Mott transition?
Well, they can really know that they know the filling quite well. I don't, because they have top and bottom gates, and they can separately tune the fillings, and they can tune the whole.
Okay, fine, I understand the argument.
So yeah,
I
to be
wouldn't-
honest, I'm not an
I
experimentalist.
wouldn't buy it if I was you, but I understand.
Oh, wait. So why would it not be?
Because when you apply these electric fields, you do a whole bunch of other things to the electronic structure.
Yeah, but if so, they have a top and a bottom gate, and I always forget like the sum or the difference is the electric field. Like I think the difference, right?
And anyway, so it's experimental evaluation of the filling factor
Yes.
of a band which is stable against other perturbations. Is that the argument?
Well, no, the band definitely changes with this electric field. That's key thing, right? So what you tune here supposedly is the effectively U over T.
Fine. So if you go to your Mott argument, he didn't assume that the band changed with the external parameters.
Well, but you need some U change, for example. You need
Okay.
some.
I was just trying to figure out what's the definition of the word Mott in this presentation.
Yeah, filling one.
Okay.
And I'd love to learn more about whether or not I should trust it, because
Okay.
that's a good point.
Very good.
Okay, so possible theories. One theory is you have one electron per unit cell. So if it's not magnetic, it has to be spin liquid. That's basically a spin-on theory, where you then the theory is you take your electron, you fractionalize it into a charge-on and a spin-on, and the charge-on is bosonic and condenses or not. So that is the difference between the metallic and the insulating side. But that requires then to have a spin-on Fermi surface on the Mott insulating side. So it has a very specific predictions for example, how the insulating gap should go to zero, or how the mass enhancement would go on the metallic side. Then there's of course DMFT, which is proposed as one of the most important numerical methods to study Mott transitions. But of course, that's something that happens in infinite dimensions very well. It predicts, let's call it a weakly first order transition, in the sense that it is first order at zero temperature, but the critical endpoint is at a relatively low temperature. So if you look at temperatures higher than a critical endpoint, it actually looks still as if it's a zero temperature quantum critical point. And then you can wonder, well, maybe it's just some more classical picture that you have metallic and insulating domains, and that can then give rise to percolation of the metallic domains, and then you have different type of, well, that's also a phase transition. If I just emphasize looking at this mass, they have very different predictions for how the effective mass diverges. So there's a logarithmic divergence in the spin-on theory, because it comes from an XY model. There is the DMFT predicts a linear divergence of the effective mass, and percolation theory actually predicts no divergence of the effective mass, because it's just metallic domains that percolate. In the experiment, they see something, an exponent that looks like between 0.6 or 0.7. So clearly, none of them are even close to what they see in experiment. So we want to explain this further, and therefore, because I focus now on the mass enhancement, let's look a little bit of what we know about mass enhancement. So, quick recap: if you're in a Fermi liquid, you typically expect that at low temperatures, there's a residual resistivity coming from this order, and then there's a t-squared behavior of the resistivity coming from the electron-electron scattering. Now, also in a Fermi liquid, we know that's a gapless state, so the specific heat has this Sommerfeld form, meaning the specific heat is linear in temperature with gamma, the Sommerfeld coefficient, which, according to Fermi liquid, according to Landau, is proportional to the effective mass enhancement. And to make this circle complete, this factor A in the resistivity is, according to the Kadowaki-Woods ratio, proportional to the effective mass squared, or to the Sommerfeld coefficient squared. So this has been seen through a wide range of different Fermi liquid materials. Yes.
So gamma proportional to m star, this is a prediction of Fermi liquid theory.
Yeah.
Is A proportional to gamma squared also a prediction of Fermi liquid theory?
No, not
Why?
because you need some extra assumptions.
So
So
can you this is an experimental plot, but can you do a calculation of A
oh yeah. So this
that explicitly demonstrates that this should be true?
yeah. I mean, you can do it, but it's not in Landau's original Fermi liquid theory.
Fine, but I mean, it's in the
Yeah, so
intervening
what you
7
can do
years.
is so in this paper, this Nature Jacko and Nature Physics paper, what they do is they have basically the same type of calculation as I did before. You just do Kubo formula without vertex corrections. You assume a certain form for the local self-energy. And we know what the local self-energy should look like in a Fermi liquid. It should be have a linear term of the self-energy that sets the mass enhancement, and it has a quadratic term that actually sets the so quadratic in energy term that sets this t-squared component in the resistivity. Now, the linear part is in the real parts, the quadratic part is in the imaginary part of the self-energy. They should be related, the Kramers-Kronig. So they use this relation between Kramers-Kronig relations to say that this A should be, the coefficient in front of the omega squared should be squared of the coefficient in front of the linear term. That's basically the derivation. But yeah, it's not as, it's a little bit more detailed and a little bit more assumptions, and kind of the effective mass, that is basically level of proof.
So the main assumption is the local self-energy.
Yes. And then there is some assumption about how you implement the Kramers-Kronig, because for true Kramers-Kronig, you also need like long, high energy behavior. So it's a bit more involved. We can go through here. So in the remaining sort of 25 minutes of the talk, I wanted to talk about a couple of these properties, namely the residual resistivity, the specific heat, and then I'll get back to the Mott criticality. So talking about the residual resistivity, right? Because I said there's this resistivity is residual resistivity plus AT squared. Now, if you just look at zero temperature and you ask, how is that changing in a correlated metal where I somehow increase the mass enhancement? I look up the book from Piers Coleman, who has a lot of chapters about heavy fermion physics in there. And there's literally this plot that says, if you have mass enhancement, right, you have your standard Druder expression for your residual, in this case, residual conductivity, but just 1 divided by that is the residual resistivity. The moment you start to increase the mass due to interactions, the size of the Druder peak is reduced to NE squared divided by M star, but the width of the Druder peak is also renormalized because the effective scattering rate for the heavier quasiparticles is also renormalized by the same factor that renormalizes the mass enhancement. So even though you're in a heavy Fermi liquid, the standard theory of heavy Fermi liquid says that the residual resistivity should not change when you enhance the mass. So if you look at the experiment, that's clearly not the case here. So you have states that you see that the t-squared component does increase, it becomes steeper and steeper, but also the residual resistivity increases and increases.
The Kondo effect and the Mott effect are completely different sectors of physics.
Yeah, I didn't mention Kondo.
Well, the previous graph was about the Kondo effect.
Well,
I'm sorry, I've read Coleman's book. This slide.
This is not the Kondo. This is the Kondo lattice, which is slightly different, right? But it's the heavy fermion regime. The only thing you need for this derivation is that you have a self-energy, which is, so the self-energy is this shape, right? So that reduces the quasi-particle peak, that increases the mass, but because you wait, let's try this. So I have kf divided by mk minus kf, and now I add this term there, and I have still my imaginary part, my scattering rate.
Okay, fine. So in terms of the Green's functions or the self-energies, you're looking at a piece of the problem which is common both to heavy fermion systems and to the Mott system.
Yes, but we're not, yeah. So, so it's always a bit confusing for me because, well, not confusing for me, but what I mean is that heavy fermions, when I say heavy fermions, I mean just a Fermi liquid with heavy quasiparticles and not necessarily the whole Kondo.
That's not what Piers Coleman meant.
True. But the Kondo part is all about this other blob.
Okay, fine.
This part still applies.
Fine, go ahead.
But residual resistivity clearly increases. What we therefore want is, ideally, we should be able to find a system that you can separately tune disorder and interaction strength and then somehow tell you whether the residual resistivity increases because of interactions or because of disorder, stuff like this. So I have a friend in Vienna, Andrei Pustogov, who says, yeah, we can do this in organic systems. So this is a very complicated formula, but what you only need to know is that this is a triangular lattice system where you can tune both the amount of interactions by tuning pressure, because what pressure does, it squishes this organic material closer to each other. Therefore, the effective hopping of your effective triangular lattice Hubbard model increases. And so if you increase pressure, you decrease the correlations. At the same time, there's these different molecules, which are visualized there on the right. If you go from one molecule with sulfur to a molecule with selenium, this is isovalent, it doesn't change the electronic charge. These molecules have exactly the same size. So the only thing that happens when you take a partial substitution of these selenide-based molecules is that you increase disorder. You just introduce some randomness into your material. So Andre made a series of these materials and put them on a series of pressures. And then we have these curves. So again, just to emphasize, this is increasing disorder. So every plot is a different level of this selenium substitution. And then if you increase pressure, it becomes less interacting. But I just put the color curves the other way around. So this dark blue curve is the highest pressure, and then lower pressure are these curves which are steeper. And this resistivity against T squared. So all of these curves have, at low temperatures, a Fermi liquid peak. So from that, we can extract how this relation is between the residual resistivity, which is basically the intercept at zero temperature, and the slope, which is this A. And for each sample, we found a more or less linear relation between the residual resistivity and this A coefficient. And that was quite a surprise for us. The way that we yes.
This organic molecule, it's a quasi 1D system or a quasi 2D system? Quasi 2D.
Yeah, so it's effectively a triangular lattice system. So this very system has been very popular because it's also superconducting. I mean, if you look carefully at some curves, you can see it become superconducting. At zero pressure, there's some talk whether it might be spin liquid or whatnot, but I'm just going to the higher pressure regime where it's just Fermi liquid. So the way that we understand this is going back to the Fermi liquid picture, basically on this level of the self-energies, which would, in a sort of more broadly friendly way, called the frequency-dependent scattering rate. So imagine you have a frequency-dependent scattering rate in a Fermi liquid, which is just something that comes from disorder, and something that comes from interactions, which is A. I just put a prime here because it's different from the A in the resistivity by factors of pi and 4, and factors that you don't want to be bothered with. But still it has this form omega squared plus temperature squared. If you now have a locally varying chemical potential, so what we imagine is that there are some puddles, which have been seen, for example, in graphene. They have not directly been visualized in these organic systems, but I think it's kind of a universal thing that disorder is not only local, but also can have more smoother variations. Then if locally, there's more or less constant chemical potential and a Fermi liquid establishes. And next to it, you have another regime, which is a different chemical potential, but also, again, locally established to be a Fermi liquid. So we can imagine that the local scattering rate, so a function of position and frequency and temperature, is just your Fermi liquid regime, Fermi liquid scattering rate, but now shifted in energy by your local chemical potential. And if you, let me finish, and then if you average over the potential fluctuations that you have in your sample, you literally get that the average frequency-dependent scattering rate has still this omega squared contribution, but it has a extra contribution that's frequency independent, that's proportional to A and the variance of your potential fluctuations. And that leads to a residual resistivity that has this relation. It has some completely local impurity dependent scattering rate and something that's linearly proportional to A, just like we observed. Yes?
Isn't it true, though, that if a chemical potential varies locally in a material which contains a fluid, and it could be any fluid, then currents will respond and they will re-equilibrate the chemical potential?
Yeah, so that would be the case if it would be kind of natural, if there's not like pinning of disorder or stuff like that. So I imagine that so usually theorists start by modeling disorder as completely uncorrelated between positions, and you have a delta function here and a delta function here that just causes bouncing of electrons. But now imagine in graphene, we know this often comes from the substrate. There's some defect in the substrate, so that gives a pretty long range potential that affects the system.
Okay. I don't think that's a thermodynamic chemical potential though.
No, I mean, so yeah, so this is a confusing thing because an on-site potential or the chemical potential, or the thermodynamic chemical potential, they kind of enter in the same way in your Hamiltonian in the end.
Okay, well,
Um,
I'm glad to learn. I had learned something else as a child, but
no, I agree, but it's to me something that we're also struggling with conceptually, how to translate this with the kind of overall chemical potential that sets the overall density. But we know so I always come back to graphene because even though there's not a Fermi liquid, so in that sense it's not relevant for this, it has been very well studied that graphene on certain substrates has this nice, exactly this picture, basically. So you would think graphene is a very well conducting system. Why doesn't it equilibrate? Because of the disorder allows it to be variations in the local chemical potential, therefore also variations in the local electronic density. Variations, therefore, if I would have that in a Fermi liquid, it would be variations in the local scattering rate, I think.
Just one remark that if this chemical, if due to pinning or else we have small dipole moments like because of charge transfer, physically I am wondering if that is a possible way to have different chemical potentials but still compensate for them, because if the chemical potential difference between across a boundary is too small amount of charge transfer and there are local dipole moments like in a PN junction, that can be a way to have different chemical potentials under thermodynamic conditions.
Okay, that's a good point.
I mean, what I mean is it necessarily implies for me that there are local dipole moments at the boundaries.
You mean like just pointing from like the high charge to the low charge?
It's like a PN junction diode. There are two, it's a system at thermodynamic equilibrium, but there is band bending because the charge transfer accounts for the fact that we can still have two different chemical potentials. But if you add a term plus E times V, then it balances everything.
Yeah.
Didn't they interpret some graphene data exactly like this?
Yeah.
In terms of like PN junctions in these puzzles.
Yeah, I mean, it's the same idea that we
Yeah.
can have, if we account for dipole moments.
Yes.
Is it important that it's omega squared plus pi squared t squared?
Oh, it's not super important, but it's just if you do the calculation, you get that. It's just comes from, very briefly, the pi comes from the fact that you do the cell calculation of Matsubaru frequencies and then lowest Matsubaru frequencies pi t. The analytic continuation, the relation between omega part is always pi. If you want to convert frequency to temperature, you always have to put in a pi. Yeah, it's not very important for this argument. So because we found this in the organic systems, we decided, does this occur in other materials? So well, actually, a PhD student went the effort and went like plowed through the literature of Fermi liquid materials, and surprisingly, or interestingly, many Fermi liquid materials, also the Condolettes, Pierce-Coleman type heavy fermion materials, seem to have the relationship that if they can somehow tune by pressure, magnetic field, the A coefficients or the effective mass, they can also see that the residual resistivity changes linearly with them. So we see in this color scale all the heavy fermion materials like the cobalt indium 5, the uranium compounds, the terbium compounds, their strontium ruthenate, which is of course also a very famous paradigmatical Fermi liquid, which also seem to scale linearly with some moray material, pnictide even, and a whole class of organics besides the one that we studied also seem to have this linear relation.
What is the small error in rho 0 minus r?
It's a fitting function. Okay. Well, so you have still this guy.
Is rho 0, okay.
So
Yeah, okay.
right, because it's not, people have sometimes people say it's not linear because it's a constant plus linear. So we just subtract this constant, and then you can put it nicely on the log.
But it is the same constant for all.
No, every material has a different.
No, within the material.
Yeah. So once you have the material, I mean that's it. I have a certain material that I can tune, and then I plot this, and I get something like this, and we draw a line, right? That's how this plot is made. And then this guy we call R, subtract it so we can put it on a log log plot.
But I thought that for some of the versions of all of these materials, you were also varying disorder.
But
Which presumably would change this constant.
if you would somehow change disorder, yes, but we assume that possible changes in disorder due to pressure, for example, you can imagine that if you put a material under pressure, the effective disorder change.
That wouldn't matter so much, but were there not cases where you were changing the stoichiometry?
No, these are all materials like one sample and we do something to it, like pressure or fields. Pressure, magnetic or electric fields. So no, if you have different samples, then it would be very difficult to put them on a straight line.
And you haven't played with irradiated materials?
No, not in this list. Yeah. So that's why also in our samples, we have 3 samples with different disorder content, and each of them fall on a different straight line. But the points of the straight line are just with different pressures. I really like the amount of questions, but I don't think I can go through all of the materials, therefore.
Since you were instructed to do 45
Exactly.
plus 15, then it's all good.
Yes, no, I'm very happy with that, and I'm here the whole day. So of course we can talk more about it. I think I have time for one topic, which is a microscopic kind of exploration of the stuff that I was talking about so far, which is going to be very theoretical. So my apologies to the experimentalists in the audience. Microscopically, the way that I want to understand Fermi liquid theory is, well, any electronic system can be understood by writing down your Green's function and then having a self-energy that should contain all the effects of the interactions. And then the self-energy in a Fermi liquid, as I mentioned before, has these most important parts is these 2 terms, which are a linear part in the real self-energy and an imaginary part in the, and a quadratic part in the imaginary part of the self-energy. This linear part actually renormalizes the mass. So what happens, I just call it B here, this factor B is related to 1 over Z, the quasi-particle weight, that's related to quasi-particle mass enhancement. And the spectral function at 0 temperature, therefore becomes just this imaginary part of that guy has this delta function of where your renormalized dispersion is, multiplied by this factor Z, which is between 0 and 1. So that tells you that not only the mass becomes heavier, so the slope of the dispersion changes, but also the quasi-particle weight itself is reduced. Now, when we started looking into this, it's like, okay, this is nice. We can start with this form of the self-energy. And the first thing that I want to do is I want to calculate the specific heat, because Landau predicted that should be proportional to the mass. So in an interacting system, you would think that it would be impossible to calculate the specific heat, because that sounds like something you would require, calculating the expectation value of the interaction energy, which is some 4 electron function. So that's very complicated. But luckily, we found in the old Soviet literature something called the Migdal-Galitsky formula, which allows you to exactly calculate the energy of an interacting electron system using only the 2-point electron, the spectral function of the electron. And for the theorists, I just want to go through the proof because it's very simple and elegant. Imagine you have a generic interacting Hamiltonian, which has I diagonalize the linear part, I diagonalize the quadratic part, and I have some 4 fermion interactions here. If I now take this commutator of my annihilation operator with my Hamiltonian, work out the math that this becomes exactly kinetic energy plus twice the interaction energy. Now a commutator between an operator and the Hamiltonian is nothing but the time dependence of that, right? That's the Heisenberg equation of motion. Now I can put expectation values around this, and now it starts to look an awful lot like a Green's function. So I can take the spectral representation of that Green's function, and I find that I can calculate kinetic energy plus twice the interaction energy is exactly given by this formula. Integral over all the states, the energy, spectral function, and the Fermi function. Then the only thing we need to do is we need to add 1 kinetic energy, which is a term that's also proportional to the Green's to the just simple electronic spectral function, divide by 2, and they end up that the exact energy is given by this expression, half times bare dispersion plus energy, spectral function, Fermi function, and then specific heat, I just take the derivative. this. Now, if you would try to calculate this for the Fermi liquid, we just happily plug in the Bayer dispersion, which is Vf k minus Kf. I plug in the Fermi liquid spectral function, which I told you is Z times the delta function. And inside there, the renormalized dispersion inside the delta function. So I integrate the delta function, I do a Sommerfeld expansion, and I get a term that's absolutely not what Landau predicted. So something is wrong with this derivation, but it's a very appealing derivation. What turns out is that I very quickly ignored a very important part in here, which is the temperature dependence of the electronic self-energy. And that was kind of a surprise, because usually you think that the specific heat, specifically the Sommerfeld coefficient, the low temperature specific heat, should only depend on quantities that are low energy. However, these are the low energy properties of the quasi-particles, but the quasi-particles themselves are dressed versions of electrons, and that's actually quite a high energy process. To give a concrete example, if I have some Bayer dispersion and I have some interactions that make it a heavier effective dispersion, and now I ask, how does the total energy of the system change as I raise the temperature? It can be that the total dispersion would change, here close to the Fermi level, but also very far away from the Fermi level. And even the electrons that are here changing, they contribute to the total energy and therefore to the specific heat. So even though from the quasi-particle perspective, specific heat is a low energy property, from the original electron perspective, it's a high energy property. So going back to this Migdal-Galitsky formula, I just try to rewrite it a little bit into two steps. I have some what I call energy density of states, which is this complicated expression, and then the total energy is just this energy density of states weighted by a Fermi function. Now this guy, the spectral function of the electrons, has a temperature dependence that we cannot ignore. So now if I want to ask what is the low temperature expansion of this guy, there will be a contribution coming from the Sommerfeld expansion of the Fermi function, but there will also be a contribution from the temperature dependence of the spectral function. So here, Landau tells us that this gamma Sommerfeld coefficient should be proportional to the effective mass. We just calculate what the Sommerfeld expansion was. So we have a new sum rule that the second temperature derivative of the energy density of states in an interacting system is proportional to the effective mass minus the Bayer mass. And we verified this numerically using DMFT on a beta lattice. And indeed, it's a function, this second temperature derivative of the energy density of states. It's a highly non-trivial function that extends to very high energies, but if you integrate over it, it does become equal to m star minus m. I think that is a moment to thank my collaborators, in particular Anna Efimova, who is the PhD student who was working on this project. Of course, my people that I work with on Mott criticality and metal insulator transitions, Simone and Sergio, Vlad and Yuting, and my organics experimentalist friends, and my Antoine and Fabian, who are helping with the DMFT for this sum rule that I presented. So I come to the end of my talk. Some of this is already online. Sum rule is not yet on the archive, but hopefully soon. And thank you for your attention.
Any further questions?
This is an experimentally fixed question that given the fact that in your scaling theories, at least for the non-interacting case, there is this assumption that the scattering time remains the same. So have the experimental papers also measured the Hall effect? Because the Hall effect will give information about the scattering time. So what I mean is it can be a way to cross-check if the reason that the scaling is matching the data. So it's another way to cross-check if the Hall effect also shows the similar behavior of the scattering time.
Well, so there is an important caveat there. That's the claim that the Hall effect has the same behavior as the Hall conductivity has the same behavior as the longitudinal conductivity, and therefore the Hall resistance should just give you the electronic density, right?
No, this is what I'm saying, that there should be a correlation.
Yeah, that there should be, but that correlation is also changing when you go to extremely low densities of charge carriers, which is closest to metal insulator transition. So if you want, I can show you some results that we have on there. you have to be careful with that statement. Just measuring the Hall effect in that regime will give you different things than you would have if you would do a Hall effect far away from the transition.
I have a small question. You always made the assumption self-energy is local, even if it's not local, will in some sense, when you were talking about the patterns in your organics, it's like to have a bit of self-energy, which is new that you may vary, but you can see there's an effect in self-energy non-local, my point of view, which is dependent on the space.
Yeah, I would still call it local if it's
right. I understand.
On every
but
base.
my question is that we know that in the low-dimensional systems, like two-dimensional, self-energy is non-local. So will not this change the picture?
So, of course, in general, it will change. The problem with non-local corrections is that it's very difficult to say anything sure about that. The Migdal-Galitsky stuff, the sum rule that I presented, we do not need the local self-energy for that. That works still with any kind of non-local because it's kind of a general proof. So that applies to any type of self-energy, also like fully momentum and frequency dependent self-energies. How this puddle picture changes when you have local self-energy, that's something that we're trying to explore. That's kind of the next step.
Because I didn't read the book of Piers Coleman as somebody else did, but there too they had local self-energy.
Yeah. I mean the key.
I know the papers of Piers Coleman. I know that so that picture will break down as soon as you assume no local self-energy.
I don't know if it breaks down, right? Because
let's put it this way: the peak that should stay constant will not be constant anymore.
When we do most people who do superconductivity also assume local order parameter in the sense that your delta is independent of k, or if it is dependent on k, it just has a very trivial form like dx squared minus y squared, right? So, but if you do a full momentum and frequency dependent Ailey-Ashberg theory calculation, you will invariably end up with the Cooper pair expectation values that are dependent on both frequency and momentum, even in simple S-wave systems. But in the end, you don't care because you only really the quantity of relevance is the gap at the Fermi level, at the Fermi momentum. So I think a lot of this behavior also, you don't really care what happens if there's some crazy momentum dependence away from the Fermi level. We just assume that the value that it has at the Fermi level, at the Fermi momentum, is the relevant one, and then we make that one kind of the local. But yeah, you're right. It could be different. I do remember that I talked with Antoine Georges about this, and he says, yeah, every time he tried to incorporate, with like, this cell or CPU corrections to GMFT that has like multiple sites, patches of momentum space or something like this. Typically, mass enhancement is just reduced, actually. So the actual Mott transition is not governed by these momentum dependence of the self-energy. It's really governed by the frequency dependence of the self-energy. That's at least what. Further questions? Then let's go for coffee and thank you.